Okay, so question 11, we have a velocity time graph for a ball bouncing vertically on a hard surface. So at what instant does the graph show that the ball is in contact with the ground for the third time? So these vertical lines represent when the ball is in contact. Now, they are vertical because of the keyword here, a hard surface, so the ball does not really spend much time at all in contact with the ground. Now, it is when the ball is in contact for the third time. That's the first contact, second contact, third contact. So here we have 2 seconds, and that there will be 2.1, so it's in between 2 and 2.1, and that is halfway between 2.05 and 2.1, so I've given 2.075 seconds, and that's where the line is vertical. Those are your 2 marks. The downward sloping lines on the graph are straight, so 1, 2, 3, 4. Why are they straight? Okay, so first of all, what does the gradient represent on a velocity time graph? And the gradient represents the acceleration. So these sloping lines represent acceleration. That's the first mark, and then it is constant. A straight line on a velocity time graph reflects constant acceleration. So those are your 2 marks. I've worked it out as well. Minus 10 meters per second squared. That's the rise over the run, and I get minus 10. And that's when you look at the context of the question, is the ball falling vertically, so it's the acceleration due to gravity, which we know is approximately minus 10 meters per second squared. It says calculate the height of which the ball is dropped, and the area underneath a velocity time graph gives distance, so the height when the ball is dropped. So here when the ball is dropped, it has 0 speed, and then it falls downwards, and that represents a negative speed, and this is where it hits the ground, so this is the point where it strikes the ground. So from there to there, that's where it's complete its fall, and we work out the area here. And that's a triangle, so it's a half base, so that's half of 1, which is 0.5 times by 5. So a half times 0.5 is the time, times by 5, and that gives us 1.25 meters from where the ball is dropped. Okay, so this section here is a little tricky. So sketch the displacement time curve on the axis below for the first second, so 1 second. So what do we need to know? We know that the ball dropped 1.25 meters. So the reason why I've put it as a negative is because the object is falling downwards, and that's a negative displacement. So that's minus 1.25, that point at 0.5 seconds. I know after 0.5 seconds the ball had dropped 1.25 meters. So therefore we know negative displacement there, minus 1.25. We've said that the initial displacement is 0 because that's where the ball starts off. Although it starts off above the ground, we call that initial point 0 displacement, and the ground minus 1.25 from its original position. So that's minus 1.25. And then the last point is, let me go back to the graph here. So the next time the ball reaches this point here, and just before 1 second, that, remember this was a falling, so this section here is the rising part. So this is at the top of the second bounce. So if we work out this area here, that will give us the height the ball bounced afterwards, and that is half times 0.4 times 4. So that there is 0.4, approximately 4 seconds, and the area is 0.8 meters. So from minus 1.25, we add 0.8, and we know it never goes back to its original height. It's slightly below that height, and that's minus around about, if you do 0.8 take away 1.25, we get 0.45. So I've marked the point minus 0.45 here. So what happens? Why is it curved? We know that the ball is speeding up, so the gradient will get higher and higher as we get closer to the ground, and then the gradient will get less and less as the ball starts to rise. So here, and then at this point it starts to fall again, so then the pattern repeats itself. And what is the displacement of the ball when it finally comes to rest? So when the ball is on the ground, so then the ball's on the ground here, initially you had the object falling from that point there. We saw that was a zero displacement. There's your ground, and that distance is minus 1.25 meters.